Hello everyone, today we're going to talk about deadlock, resource allocation graph and the safety algorithm. So let me introduce us to you first. We are from Team Quality Engineers and hopefully you will like our video. So before getting started, a very special thanks goes to our professor, Dr. Zuria Hati. Hello everyone, my name is Ayaz and now I'll just start the video with a brief introduction of deadlock. So what is deadlock? A deadlock is a situation where each of the computer process waits for a resource which is being assigned to some other process. Doesn't it make sense? Let's take an example of real deadlock situation in an operating system. This is a diagram for deadlock situation. In this situation, none of the process gets executed since the resource it needs is held by another process, which is also waiting for other resource to be released. Therefore, P1 and P2 doesn't execute. Okay, let's see how deadlock occurs in operating system. A deadlock situation can arise only if the following four conditions hold simultaneously in a system. Let's see. 1. Mutual exclusion. 2. Hold and wait. 3. No preemption. 4. Circular wait. Let's take one by one. Number 1. Mutual exclusion. Two processes cannot use the same resource at the same time. Number 2. Hold and wait. A process waits for some resources while holding another resource at the same time. Therefore, process 3 cannot access the resource 2. Number 3. No preemption. The process which once scheduled will be executed till their completion. Therefore, process 2 cannot access the resource. Number 4. Circular wait. All the processes must be waiting for the resources in a cyclic manner, so that the last process is waiting for the resource which is being held by the first process. If the system will be able to violate one of the four necessary conditions of happening deadlock, it can prevent the deadlock. How to do that? Number 1. Mutual exclusion. But these are not practical. Number 2. Hold and wait. But these are also not practical. Number 3. No preemption. This is also not practical. Number 4. Circular wait. This is practical. Now let's move to the next topic.
Assalamu alaikum, my name is Jami Sharir and today I'll be talking about resource allocation graph. Okay, so uses for resource allocation graph. Resource allocation graph can be used for deadlock detection and deadlock avoidance. Alright. Okay, some features of resource allocation graphs. The first feature is they are directed graphs. Okay, and the vertices are labeled as V and the edges are labeled as E. The second feature is the vertices can be processes P or resources R. The third feature is edge can be either requested edge, which is the arrow that goes from process to resource, or assignment edge that goes from resource to process, the arrow. The fourth feature is the diagram elements representation, which is processes are represented by circles and resources are represented by rectangles. Alright, so let's look at an example to understand this further. So two processes P1 and P2 are given, and then two resources R1 and R2 are here. So if we look at the dots inside the resources, these are instances of resources that are going to be called by processes. Later on we'll see that. Okay, so here this is a requested edge. This is because process P2 is asking for request R2, an instance of request R2. Alright, here we'll see assignment edge, which is an instance from R1, from resource R1 is being used and is being passed on to process P1. Alright, so let's look at the resource allocation graph algorithm. The first thing that we have to take notice is this is applicable if each resource has only one instance. So basically, inside the resource there will only be one instance. There will be claim edges from process to resources. Processes might request resource in the future, so claim edges are represented by dotted arrows. When a process requests resource, claim edge will be changed to request edge. Request edge will be converted to assignment edge only if the conversion does not lead to the formation of a cycle in the graph. Alright, let's try to understand using an example. Suppose P2 requests for R1. Can this request be granted? Okay, so the first thing we'll have to look at is, can R1 be assigned to P2? Here it is R1, and can it be assigned to P2? Okay, so let's look at this. Here, process P1 is using resource R2, and process P2 is requesting resource R2. So P2 is requesting resource R1, so let's change claim edge to request edge. So this claim edge will be changed to request edge. Alright, the claim edge has been changed to request edge. Request edge can now be changed to assignment edge. Alright, so request edge has been changed to assignment edge, and the resource R1 is now assigned to P2. The next question we have to ask ourselves is it not cyclic? So if you look at the graph, we can see that and the arrows are forming a complete circle, and so it is not true, and this is cyclic, and as a result, request for R1 to be allocated to P2 cannot be granted. Okay, let's look at another example. Suppose P1 requests for R1, that is process 1 requests for resource 1. Can this request be granted? So process 1 will be requesting for R1. So let's see this. Process P1 is again using resource R2, as we can see, and process P2 is requesting resource R2. So P2 is asking for resource R2, and so the first question we have to ask is, can R1 be assigned to P1? That is R1, can it be assigned to P1? So let's change claim edge to request edge, that is the dotted arrow will change to solid arrow, and then let's change the request edge to assignment edge, and resource R1 will now be assigned to P1. And now we have to ask the question, is it not cyclic? So we look at the arrows again, and we can see that it's no longer cyclic, and so our answer will be yes. And finally, request for R1 to be allocated to P1 can be granted, so resource 1 can be allocated to process 1, and in this way we can use resource allocation graph for deadlock avoidance. That's all. Thank you.
I'm Megla, and I'll be talking about safety algorithm in deadlock avoidance. But before we get there, what is deadlock avoidance? So, what deadlock avoidance does is that it ensures that the system never enters an unsafe state. Okay, so safety algorithm is something that helps with ensuring that the system never enters an unsafe state. And if you're wondering what the safety algorithm is, we'll just get there. It is the algorithm that is used to find out whether or not a system is in a safety algorithm. That is its main essential job. So now that we know that, if we find the safe sequence, deadlock is not present. But in case we don't find a safe sequence, it means that the deadlock is present. And what is this algorithm and how does it even work, if you're wondering? We'll get there just right now. So first what we do is we initialize, we set work to available, and we set finish I to false. This means that all the finish flags are set to false for all the values of I. Later we try and find an I for which the finish I is set to false and the need I is less than work. If it does not exist, we go directly to step 4. But in the case where it does exist, we set work is equals to work plus allocation. Allocation is basically the processes which are allocated indeed, and we set the finish flags to true. After that we go to step 2 again, and we find the finish flags and set them to true one by one. If finish I is true for all of the I's, then the system is in a safe state, otherwise it's not in a safe state. That will be it, and thank you for your attention.